Hello, in this video we will talk about principal component analysis. So principal component analysis, also called PCA, is a method technique that is widely used to transform data to a new dimension. So for example, original dataset has 13 columns for the 13 variables, but in the, for example, machine learning, the dataset can be too large to fit into the machine learning algorithm. The computation cost will be very high if we use all the 13 variables, 13 features. So one way is to remove some variables, but these will lose much information. So principal component analysis can be feasible that we can transform the original data set to a new data set, for example, with 3 columns. And these 3 columns, each one called principal component. And the first one, direction, means the direction capturing the largest variance from the original data set. And second principal component will capture the second largest part of the original dataset's variance, and so on. So we will get this smaller dataset and simultaneously will not lose too much information from the original dataset. So, for example, this is the original dataset, D dimension, and we use a matrix. The matrix has a shape D times K dimension for D row, K column. Then original dataset X times this multiplied with this matrix. This is transformation matrix, and we'll get the result Z. So Z is a new matrix, new dataset with K dimension. So here K usually is much less than D. Right? So, for example, K is 3, but D is 13. And the steps of implementing our principal components, step by step, is first we will normalize or standardize the D-dimensional dataset. So each feature will have the same scale, usually with the mean 0 and standard deviation 1. Then we will construct a covariance matrix from this dataset, and the covariance matrix is a square matrix with a row and a column equal to D here, right? So this will represent the pair-wise covariance information of each variable pair from the original dataset. Then using linear algebra technique to get the eigenvectors and eigenvalues from this covariance matrix. So usually we'll get, for example, D-dimensional, we will get D eigenvectors and D eigenvalues. So each eigenvector is related to 1 to each eigenvalue. And if we rank all eigenvalues from the highest to the lowest, then the first eigenvalue will represent the largest part of the variance it will capture. So we will take, for example, only several eigenvectors with the largest eigenvalues. For example, we take 3 eigenvectors, then we'll get this together with the matrix. This is the transformation matrix. Then you can, for example, here k is 5. So we get 5 columns and D rows of this matrix because each eigenvector has the length of D. So if we column-wise combine these eigenvectors, so the matrix will be D row and K column, right? Then it will be easier that we will multiply original dataset with this transformation matrix. We'll get the final new dataset with d-dimensional datasets. So next we will show example using Python code. So if you are interested in the code file, you can download this file from this link. And we also have a website, rdatacode.com, for Python and R training if you are interested in. This is a paid course on weekends, Saturday and Sunday, about 8 hours total. So next we go to Python programming. This is chapter 5 file. So first we just set the working directory and load all the packages. Some packages may not be used because this file is quite large, not only for principal components. So we skip several parts. Then we download a file called OneData. And from this link, and we use header none and with the pandas read CSV function to read this link directly. So the result is a data frame, and we set this data frame with the column name. Then we show this data frame's first several observations. So you can see there are 13 here, not shown here, but there are total 13 column name we set here, and this first row, second row, third row, right, and so on. So next we will get, because we show this example in the machine learning, so we will get X and Y. X is the feature data, will be trained this data, and Y is the label. Observe the label. So we use iLocation function to this dataset, and we'll use the second column and on second to the last column for the training features, and the first column for the label. Then we also set training data and test data with 30% of the original data for the tests, and we keep the distribution of label classes using stratified equals y. So next we will standardize this data, so using standard scalar function class. Then we will use fit transform for the training data and use transform for the test data. So both training data and the test data are standardized with mean 0 and standard deviation 1. So then we can create a covariance matrix for the training data. We just train std.t means transpose. So we can use linear lg.eigenvalue. This package is eigenvalue to get eigenvalues and eigenvectors from this covariance matrix. So we will show the eigenvalues. So you can see there are total 13 eigenvalues. And we will sum together for these eigenvalues. Then we will sort eigenvalues then this is the cumulative for the eigenvalue sorted. Then we will plot bar. We want to do this to show that the eigenvalue also represents the variance they explained. So the first eigenvalue largest and the second largest and so on. And this is the cumulative variance they explained. And the total variance explained is 1. This is a scale, the ratio. So for example, this is the largest eigenvalue, and this also represents the same proportion of variance it will explain. And this is second largest, also with this same scale for the ratio of variance from the original dataset they will explain. So next we will create a list of pairs for each eigenvalue and each eigenvector. Then we rank this pair with the value of eigenvalue from the highest to the lowest. Then we will create a transformation matrix W. Here we use 2 eigenvalues. So first, the 2 eigenvectors will be make as a first column and a second column of this matrix. Then we show this matrix. So this is the transformation matrix. 13 row, 2 columns. So we only use 2 eigenvalues, 2 eigenvectors. So the resulting principal components will have 2 principal components for the new feature. So we can use the original training data times this matrix. You can see, for example, this is the first observation of the original training data. The result is this one, is 2 feature. So the new observation, the first observation has 2 variables because we transformed from 13 variables to 2 variables. So next, we will show this new data because we will transform all the training data to the new space. And we will show new data sets along the first and the second principal components. You can see that this is the first feature, second feature of the new data set, and the training data has 3 classes, right? They also get very nice grouping. So which means we also transform the data to a new space, but it will also available to get a classification for this data. So we just show the step by step, but actually in Python, their PCA, because we have loaded many packages, right? So their function called PCA, you can use directly for what we have done step by step. So we just create an instance in Python. This is instance of this class. Then we can use this instance to fit a transform, same as we did the last step. And we can also show the variance they represent from each eigenvalue, same as before. And we can also plot the bars using this new method, directly use PCA function. So this is the same as before, same as what we use step by step. We will show also just use PCA equals n components 2 because we only selected 2, so we use option here with 2. And we will transform to the new data feature space. Then we plot same as before, although it will not use the same colorful, but actually the data shape is the same as what we did step by step. So this is the basics of the theory or implementation of principal component analysis. Thanks for watching.